Welcome to our third part of Lecture 1, and we're going to continue on looking at orbital shapes. So we've learned what orbitals are, and we've seen that they have different designators, and it turns out that those different equations that give us solutions to the Schrodinger equation give us very distinct orbital shapes from those probability densities. And orbital shapes are very important when we start looking at bonds that form between atoms when we want to make molecules. So the reason for that is because the bonds that form between atoms when we're making molecules are formed by the overlap of atomic orbitals. And so where those atoms are and where those orbitals point determine where we can form bonds. So the shapes of those overlapping orbitals will determine the shapes of our molecules. And the shapes of molecules is very important when we're looking at things like drug delivery or sometimes catalysts for certain chemical processes. So let's take a look at the different shapes of some of our different atomic orbitals. We have the s orbitals where our L value is equal to 0. Our s orbitals are spherical in shape. We generally represent them at a 90% probability density. Sometimes you'll see 95. The higher the probability density goes, the larger the s orbital has to go. So what that 90% probability means is, if you can imagine a sphere of a certain size, we have a 90% probability of finding the electron somewhere within that sphere. If we want to go to a 95% probability, we need to make the sphere a little bit bigger. Okay, if we wanted to go all the way to a 100% probability, we would actually have to go all the way out to the end of the universe. And we'll see why that is here in just a little bit. But there's what our general s orbital looks like. It looks like a ball, and that's essentially what it is. It is a spherical orbital shape. It does give us a radial probability of going from the nucleus pretty much out to infinity. And so here we see that right at the nucleus we have a 0 probability, and as we go out just a little bit we have a maximum probability of finding electrons out at 52.9 picometers, which is still really close to the nucleus. And then as you go farther away, it drops off very quickly, and this continues to go out. And while it looks like this line is actually at 0, it's not truly at 0, because that is an exponential decay. That means that it never actually reaches 0. So there is a small probability that one of the atoms in your body actually has an electron hanging out somewhere around Jupiter or Pluto. Unlikely, but it is possible. And so that's why we have that, we have to put that 90% probability in there kind of to set where we want the end of that orbital to be. So a 90% probability, I'm just guessing here, probably hits right around there, and then the other 10% is everything after that. So again, we see that maximum probability at 52.9 picometers. And like I just mentioned as well, that probability tapers off, but never actually reaches 0 because of that exponential in the wave function. Now, if we go out to our n equals 2 s orbital and our n equals 3 s orbitals, because they are still s orbitals, they will also still be spherical, but the math and the wave function shows us that they possess nodes, and these are regions of 0 probability density. So there's actually a distance where you have a 0 probability of finding the electrons. And another way of looking at that is if you have a wave going through from wagging a rope up and down, you have, if you can imagine, right in here is your zero probability. You have maximum probabilities here, or I guess here, as it goes up and down. But right where it crosses that 0 line there, that's kind of like an amplitude of a wave, and that's really what we're using that probability density as. That's the amplitude of the wave at that point. And so where that probability density crosses that 0 point, we have a zero possibility of finding an electron. And since we are dealing with an exponential as well as a sine wave, that sine wave does in fact cross a 0 point. So we do get regions of zero probability density. And here we see our psi squared probability density here. So for the 2s, where n is equal to 2, we see a node right there. And so this represents a little region right in there with a zero probability density. And so the interesting thing I always think about is you can have an electron that goes from somewhere in here to somewhere out here, but it cannot cross this line right here. So it can go from one distance to another distance, but can't go at one point that's somewhere in between. I always find that really interesting. If we go out to the n equals 3, we now have 3 nodes of probability density. So if we look at this bottom one here, at total radial probability, or probability there, you can see that we have 2 nodes there in 2 regions where we have a zero probability density. If we went out to the 4s orbital, we would then have 3 nodes of zero probability density. Another way of looking at that is the first instance of an orbital has no nodes. After that, the second, third, fourth always has nodes kind of equal to 1 less than the number of times it's already appeared. So like for the p orbitals, those start occurring in the n equals 2 orbital, because that's where L can start to equal 1. And so the 2p is the first instance of that type of orbital, and it has no nodes. But if we go to the 3p, that's the second instance, the 3p orbital would in fact have a node. So just kind of interesting there. So let's look at our p orbitals just really quick. As I mentioned just a moment ago, they do start when n is equal to 2. And that's because L is equal to 1. When n was equal to 1, we could not have an L value equal to 1, which is why we have no 1p orbitals. We can only start with 2p orbitals. So we can have a 2p, a 3p, a 4p, a 5p, etc. They are symmetric within a plane, so they reflect upon one another. They do have 2 lobes of electron density. They look a little bit like a 3-dimensional infinity sign, if you can imagine that. They do have a natural node at the origin that's different from the probability node that we were just talking about. And we do have 3 p orbitals per sublevel, or m sub L. So remember, your m sub L can go from minus L to plus L, and those represent the different orientations you can have for different orbitals. So with an L equal to 1, we can have an m sub L of minus 1, 0, and plus 1. And these different m sub L values indicate a different axis along which those p orbitals point. So we have a px, a py, and a pz. So you have a 3-dimensional infinity symbol pointing along the 3 axes, the 3 coordinate axes. For our d orbitals, things start to get quite a bit more complex. Our L value is now equal to 2, and the first instance we see of d orbitals start with the n equals 3 level. So there's no such thing as a 1d orbital. There's no such thing as a 2d orbital, but they do start with 3. So we can have a 3d, 4d, 5d, etc. So because our L value is now 2, we can go anywhere from an m sub L of minus 2 to plus 2. And so we have 5 different possible d orbitals. These have 5 different orientations and shapes. 4 of those orbitals have a cloverleaf shape that have 4 lobes and 2 planar nodes. And then one of the orbitals has what looks like a p orbital surrounded by a donut. And so with the 4 orbitals that have a cloverleaf shape, 3 of them are oriented in the planes that bear their names. And so you have the dxy orbital. This is a 4-lobed orbital that lies in the xy plane. Those lobes you'll actually see go between the axes. Same for the dxz and dyz. The fourth cloverleaf shape is kind of a strange looking shape. Well, it's the same shape, but it has an interesting formula. We call it the dx squared minus y squared. And rather than have the lobes lie in a specific plane with the lobes between the axes, it lies in the xy plane, and its lobes are actually on the xy axes. And we'll see pictures of that here in just a moment. And I mentioned the dz squared orbital looks like a pz orbital, so it looks like a two-lobed orbital like we have with the pz. However, this one has a donut right around the center of it. So here's an example of our d orbitals here. So here's the dyz. You can see these four lobes. I can probably use my laser pointer here. So these four lobes here lie in the yz plane, and we can see that the lobes of electron density, probability density rather, fall between the axes. Same for the dxy. We see it's in the xy plane, which is difficult to see with this orientation. And those lobes, again, would lie in between the axes. Same with the dxz. It's going to go up that way, down that way, and here. Our dx squared minus y squared, you can see it shifted just a little bit if we compare the two views right there. You can see that the lobes are rotated by 45 degrees. And then we have the dz squared orbital, which is, I mentioned, it looks like a pz orbital, which looks something like this. And then we've got this little donut that goes around there. So very interesting shapes. If you go on to some higher levels of chemistry, especially inorganic chemistry, you start looking at these d orbitals significantly. They do come into play with the chemistry of transition metals quite extensively. These are the orbitals that are being filled with electrons as we enter the transition metals. So that finishes out our third portion of Lecture 1. If you have questions on this, you can refer to your textbook, and if you still have questions, make sure you contact me.